Swayam Prabha. Digital India. Educated India.
So, what we will cover today is a couple of concepts. One is instantaneous power flow, and the context of utilizing this idea is, as we had seen in the last class, we had talked about two concepts, kinetic energy density and potential energy density. And so the other concept is instantaneous power flow, that at every given point of time, if you have an acoustic circuit or an electrical circuit, what is the instantaneous power at that point of time. So we know that volt is real j omega t, and I can generalize it as half real then V E j omega t plus V star, which is its complex conjugate, E minus j omega t. Okay. Similarly, current, and the reason we are talking about voltage and current is that we will draw these analyses into the acoustic domain later. So this comes in handy, is real component of I E j omega t equals half real I E j omega t plus complex conjugate. Oh, I missed, yeah, complex conjugate E minus j omega t.
So we do not need to write real part because it will already be real because we are writing conjugates.
You're right. So as you guys rightly pointed out, we don't have to explicitly write real, because when I add these two, V and V star, it does give me the real component. So my power equals, and then I use this capital letter, uppercase letter PT. So it's a function of time, is basically a multiple of instantaneous current and instantaneous voltage. So remember, we are talking about instantaneous power, and that is basically a product of instantaneous voltage and instantaneous current. If I have to do average power, I cannot multiply voltage and current, but when I am talking about instantaneous power, it is a valid thing to multiply instantaneous voltage and current. So you have real V E j omega t times half of real I E j omega t. Okay. So if I expand that relation, I get this long relation. So it's 1/4 V I E 2 j omega t plus V I star plus V star I plus, then I have another component which has both stars, E minus 2 j omega t. So if I expand on Vi star and V star I and I add them up, essentially what we will find is that the real portion of Vi star is same as real portion of V star I, and the imaginary components are negative of each other, so they cancel out. So we know that real of Vi star equals real of V star I, and imaginary portions of Vi star equals minus imaginary portion of V star I. Okay, so these two guys, I can club them up and I can just sum them up and say that this is Vi star plus V star I is twice of real of Vi star, something like that. So I get power is a function of time 1/4 V I e 2j omega t plus I get V star I star e minus 2j omega t plus 1/2 real V I star. Okay. So now what I will try to do is I will try to simplify this term. I have simplified this term. This has been taken care of. I have to simplify this term. So again, if I expand and if I expand V star I star, oh, I'm sorry, E minus 2j omega t, then I will again see that when I add up the real and imaginary components together, imaginary components, you can do this math in your home. The imaginary components cancel out and only the real portions survive and they are same. So basically what I get is the final expression is power, which is a function of time because it's instantaneous power, is half of real portion of V I e 2j omega t plus half real portion of V I star. Okay. This portion, its average value is not 0 unless the resistance in the circuit is 0, then there won't be any power dissipated. So this portion, the average value is not 0. Average value is not equal to 0. This portion, it's a cyclic quantity. So when I average it over a cycle, complete cycle, which is 2 omega t, over a cycle of 2 omega t, then it adds up to 0 when I average it over a period of time. So we will now see an example. What we will do is we will take two examples, one with a circuit which has pure resistance in it and another circuit which has a resistive load and also an inductor, and we will see how instantaneous power changes and also what it tells us a little bit more and how we can relate it to acoustics and also transmission lines in general. So let's look at this circuit. So I have a voltage source and it has a external resistance and I'm closing the circuit. The current is I and my voltage, which is a function of time, is, let's assume, 100 cosine omega t, and omega, let's say, is 60 hertz or 60 times 2 pi. So 60 is the frequency. And the value of this resistance, let's assume it to be 100 ohms. Actually, I will change my mind and I will make this only 10 volts, 10. So it is 10 cosine omega t. So my power, instantaneous power, is half real Vi star. So my V, that is the magnitude of this whole thing, is 10, right? So that is 10 times I star. So I is V star over Z star. It just happens because this is purely a resistive circuit, so V star and V are same, and Z star and Z is same as R, which is 100 ohms. So 10 over 100, that is I star, plus, and then I have a cyclic component, real VI e 2j omega t. So V is 10 times I is 10 over 100 e 2j omega t. So if I do all this math, I get 0.5 plus 0.5 cosine of 240 pi t. So again, this is a constant dissipation of power, half watts, that is being dissipated constantly, and this power is a cyclic thing. So in part of the cycle, energy gets stored by the system, and another part of the system, energy gets dumped back into it. Does not get dissipated, it gets dumped back into the system. So it stores and releases the energy, going back and forth. The other thing you will note is that the frequency of this is twice the frequency of voltage or current, or in acoustic domain, whatever is the source signal's frequency, it will be twice that. So if I plot this whole thing, my plot will look something like this. This is my time axis. This is the total instantaneous power, which is PT. So my axis, when I plot it, 0.5, 1. So it will vary from 1 to 0 to 1 to 0, and so on and so forth. And a complete cycle will be twice, 2 times t, which is t is the period of the voltage cycle or the current cycle. We will do one more example. So here we have the same voltage source. I have an external resistance which is connected also to an external inductor. This is resistance, this is inductance, this is voltage source. Volts equals, let's assume 100 cosine omega t. R equals 100 ohms. Oh, I did a mistake. So this is again 10. Also the value of inductance is 1 over 1.2 pi henries. I am assuming that number. So my impedance of the whole circuit is Z, is basically 1 over R plus 1 over SL, and I take the inverse of this, and I know that S equals J omega equals 2 pi times 60 times J. Yeah. So my Z becomes, if I do the math, basically I get 1 over 100 plus 1 over 100 J, and then I have to take inverse of this, equals 1 over 100, I take it out, 1 plus 1 over J. So then I have to do the inversion of this entire thing. So my impedance is 100 over 1 minus J. Now if I look at the denominator, it is basically, there's a constant, a real portion to it and an imaginary portion. And I know that if I use the complex principles, I can express 1 minus j as square root of 2 times e minus pi over 4j. So you have your real component, which is 1, then you have the imaginary component minus j. So that's your so the magnitude is root 2 and this is the angle, so e minus j pi over 4. Okay, so my z is 100 times root 2 e minus j pi over 4. Everything is in the denominator, or it's 100 over root 2 e j pi over 4. I bring it up in the numerator. So my z star is complex conjugate of z, so which is 100 over root 2 e minus j pi over 4. Okay. So now I can use z star to evaluate what is I star. So I star equals v star over z star, root 2 over 10 e j pi over 4. That is my I star. So moving on, I go back and start calculating power dissipated. So instantaneous power equals half of real component of V I star plus half of real component of V I e to j omega t. So this I get as half real component of voltage is V is 10 times root 2 over 10 e j pi over 4 plus half real component of 10 times root 2 over 10 e minus j pi over 4 e to j omega t, where omega is 125. So I get, if I take the real component of thing, I get 1 over root 2 times real component of exponent of j pi over 4 plus again I get 1 over square root of 2 real component of exponent of j omega t minus pi over 4 going back, e j pi over 4 is cosine pi over 4 plus j sine pi over 4. The real component is cosine of pi over 4, which is 1 over root 2. So that becomes half, and then the oscillating component of the power is again 1 over square root of 2 cosine omega t minus pi over 4.
2 omega t.
Yes, 2 omega t minus pi over 4. So again, this is my average power, and this power, this component of power is fluctuating, and there's a phase difference of pi over 4 here. So now if you plot this entire expression, you will see that power, instantaneous power, not the average power averaged over a whole cycle. Instantaneous power can become positive and also it can become negative. But the fact that it's becoming negative is not that it's getting absorbed permanently somewhere. It's getting saved into system, and then it gets dumped back into the system back and forth. So if I plot it, my graph will look something like this. So this is my time axis, and this is my vertical axis is, let's say, watts, so power, and so it will so the maximum value will be half, and then cosine 2 omega t minus pi over 4, at the maximum it will become 1. So half plus 1 over square root of 2, that is the maximum value. So that's the maximum value, which is half plus 1 over square root of 2. Now at t equals 0, the value will be half plus 1 over square root of 2 cosine pi over 4, right? So it will be half plus half, that is 1. So at time t equals 0, this is there, and then my power cycle will look something like this. And so on and so forth. So in certain parts of the cycle, energy is getting stored into the system. In some other parts, energy gets dumped back into the system. But the average power dissipated does not change from a purely resistive circuit, which is half watts. Even though peak power does shift, and it does exceed 1 watts because of this number. So this is something we have to understand also, because we will be mapping some of these concepts into the acoustic domain as we move on, which you will see either in the next class or the class after that one. So again, average power remains same if the resistive load does not change. The other thing is that peak value can shift because of presence of inductors and capacitors, or because of presence of elements in the circuit similar to inductors and capacitors. And the third thing is, and it has a strong bearing especially in the electrical domain, is that this term V over Z, so V is voltage, Z is the total impedance, that basically influences the total current, right? Now Z in a purely resistive circuit we saw was 100 ohms, but in case of the other circuit where we had an inductor, the magnitude of Z was 100 over square root of 2. So it was not 100 ohms, it went less than 100 ohms by a factor of 1.414. What that means is that in general the circuit is drawing more current into the system. Now in transmission lines, and this does not have a strong bearing on acoustics itself, but it's worthwhile to know. In transmission lines you have a power generator unit, and that current gets transported over, let's say, 1000 kilometers, and it comes to your home. If your home has a purely resistive circuit, then it will consume some amount of watts. If your home has resistors and also, let's say, inductors, it will still eat the same amount of heat, but it will draw more current. What that means is that the heat dissipated along the transmission line goes up significantly. And most of the loads in your houses, what do they have? Your refrigerator has a motor, it has an inductor. Vacuum cleaners, they have inductors. Mixie, it has an inductor. Most of the circuits in household appliances, television, it's an electronic device, but it also has inductors. Most of the circuits which have motors, they have inductive loads. So what that means is that it draws more current. So what that means is that the heat dissipated in the transmission lines goes up. So basically the overall efficiency of the system goes down. So what people do is they try to rectify by putting some capacitive load also in parallel to the inductor, and that kills the influence of inductive load so that the current comes back to the original number. So that we will very quickly capture and see what happens. So if I have a resistor, an inductor and a capacitor, and let's say my R is 100 ohms, L again is 1 over 1.2 pi, and capacitance is 1 over 12,000 pi, then my total inductance, total impedance will be 1 over 100 plus 12 pi over j times 120 pi. So this is the inductive part plus 120 pi j over 12,000 pi, and then this whole thing I have to invert it. And if I do the math correctly, it again brings the overall system impedance to a purely resistive number, which is 100 ohms. So by adding a capacitor, you can change the phase back to 0 degrees. Similarly, if you have a predominantly capacitive circuit and if you want to reduce the power consumption in an overall sense, then you put some inductors, appropriate value of inductors, and you can bring it back. So in this context, there's another term, and it is called power factor correction, and this is also used in acoustic area, so it's good to know that. So it's power factor correction. So we know that we saw that power is half real component of V times I star plus half of real component of V I e 2 j omega t. So this is half real component of V star over Z star plus this oscillating component, and I know that V star is square of the magnitude of V, so I can bring it out. Now let's say that Z is magnitude of Z times E j psi. So if I plug this relation in here, I get V square, magnitude of V square over 2, and then I get real component of, so I will still have, and then 1 over E minus j psi, and then the oscillating components, right? And so it becomes V square over 2 into 1 over magnitude of Z times cosine psi plus other things. This number cosine psi is power correction factor. If psi is 1, then my transmission losses in the circuit are minimized. It's not psi, cosine of psi is 1, then my transmission losses get minimized. If it's more than 1, not more than, if it's more than, if psi is more than 0 degrees, then I start seeing losses in the circuit, especially in the transmission. So there are countries, especially in Europe, which have legal requirements for all product manufacturers that if you have to buy a refrigerator, it has to have this correction factor built into its system, so that transmission losses in the country do not get big, do not become large. In India, we lose about 5% of total electricity just because of this power correction factor. So we have this nuclear deal, and all these nuclear plants will be coming up. The total energy generated by these plants will be something equivalent to if we just fix one small power correction factor in our product, that much energy can be conserved by one change. So wanted to share this. So we have seen electrical power at an instant of time. So now we map the same idea into acoustic domain. Now in acoustic domain, it happens that we use pressure and velocity. So pressure times velocity is essentially not energy but energy per square, not power but power per square area, if you do the dimensional analysis of that. So a lot of times people use the term acoustic power, but what they are in reality implying is instantaneous power per unit area. So you have to be careful that when you are doing the math, that scaling happens accurately. So acoustic power, this common language again, it's essentially basically power per unit, instantaneous power per unit area. So let's call that W, acoustic power. So is so it's basically a dot product of pressure at a given point in time times velocity. So that is my instantaneous acoustic power per unit area. And again, the velocity and pressure variables, they have to be normal to each other. So if pressure is acting on this plane, the velocity has to be normal in this direction. So I expand this actually. So I know that T x t is real component of E x omega E j omega t. Similarly, Q x t equals real component of U x omega E j omega t. So I substitute these pressure and velocity functions back into the equation for W, and what I get is W x t equals half real E dot U star plus, so remember I am using exactly the same analogy which I had in electrical engineering, P dot U E 2j omega t. Okay. So now what we will do is we will evaluate what is the power dissipated in a closed tube and also in an open tube of infinite length, and see how it works out. So we will go to a closed tube. So I have a tube closed at this end. It's a rigid perfect closure, so everything is getting reflected such that reflective coefficient is 1, and the thing is getting excited by a transducer here like this. This is my x equals 0, here x equals minus L. My input excitation is that at x equals minus LT, the velocity is US, it's a pure number, cosine omega t. So in complex notation I can write that as real component of US E j omega t. Okay. So I calculate instantaneous acoustic power per unit area. So that equals half U z, that's my pressure, right, times U star plus I missed real. Real component of u z, which is the pressure function, times velocity e to j omega t. Now we know that impedance in a closed tube we had seen in earlier classes at minus L omega equals minus j z naught cotangent of omega L over c. So my power equals 0 plus us square over 2 real component of a very big number, very big term, j z naught cotangent omega L over c times e to j omega t. So my acoustic power is 0 plus us square over 2 cotangent of omega L over c sine 2 omega t. So in a closed tube, the total acoustic power being dissipated, if there are no dissipative losses, in our wave equation we assume that there are no dissipative losses happening because of the medium, is 0. Average power being consumed by the system is 0. However, energy transfer does happen between potential and kinetic states. So my plot for the power would be something like this, where this is time. So this will correspond, this distance will correspond to twice the frequency of the excitation frequency. So we will do one more example, and that is of an infinite tube. And again, I am exciting it at this location through a velocity source, x equals 0 at this location. So also I know that at x equals 0, velocity equals us cosine omega t, and in complex notation I can write it as real component of us e j omega t. So again, instantaneous power per unit area is half real u times z times u star plus half real component of uz times u e j omega t, closing the bracket. Yeah?
In the previous expression,
Hmm.
so when omega L by c, there was a term containing cot omega L over c, and this omega L over c becomes like sometimes like becomes an integral multiple of pi. There is something called infinite power.
So again, it will transfer between kinetic and potential energy
Yes,
states.
sir, but the term will become infinite.
Theoretically, because you are assuming that damping is not happening. So even in purely spring mass systems, when you excite it at a resonance, theoretically, so I'm again giving you a parallel analogy. When you excite a system which has a which is purely having a mass and a spring, at resonance the displacement goes to infinity. Right? But that doesn't mean that the energy required to induce that kind of thing has to go to infinity, because it gets compensated by it fluctuates between kinetic and potential energy state. So all is what is happening is energy transfer from potential to kinetic and kinetic. So going back, that's my acoustic power per unit area is half real, and then I get us square times Z plus half real US square times Z E j omega t. I missed a 2 here, again 2 here. So again I have US square over 2 real component of Z plus US square over 2 real component of Z E 2 j omega t. Now we know that for an infinite tube, Z equals Z naught equals rho naught C. We had seen this, right? And it stays constant throughout the length of the tube. So if I make this replacement, then instantaneous power equals US square over 2 Z naught plus US square over 2 Z naught cosine omega t. So here average power is non-zero, and this is the oscillating component of the power. So in a closed tube, we saw that because all the energy gets reflected by the closed end surface, the consumption of power by the source point at the source point is 0. But here, because you have infinite tube, and if I am exciting a membrane back and forth, that energy travels, keeps on traveling and never comes back. So my average power consumption is non-zero. So physically also it makes sense, even though in both the situations you don't have any dampening happening.
Please explain this once more. Or the physical interpretation in a closed tube and an open tube.
So if you have an infinitely long tube, you have a membrane in an infinitely long tube and it's exciting air. So that membrane is initially exciting air at this location, then after some time it excites air at this location. So it has to induce kinetic energy and potential energy in medium which is infinitely long. So it will keep on consuming power. That energy will not come back to it at all, because the tube is infinitely long. If you have a tube which is closed at the end, then that energy comes back. It gets reflected because this T minus is non-zero. So then the energy required to excite is not non-zero. It's 0 in that case, in a closed tube. Even though in both the systems you have no dampening. So this is what I wanted to capture today in terms of instantaneous power, and also in about how it relates to acoustics, how it helps us understand total power consumed in an open tube, in a closed tube. The other thing I wanted to share with you is a brief introduction to how transducers, acoustic transducers are made, so that you become familiar with the structure of it, the notion of transduction, and then how do we start establishing equivalences between electrical and mechanical components. So we'll just for a few minutes go over this, then in the next class we'll go deeper into it. So what you have here is, let's say you have a metallic structure, what I call frame. This is made of metal, on which the whole transducer or the speaker, loudspeaker, is mounted. So this is a metallic structure, and this is, I have made a cross section, so you can rotate it by 360 degrees and you will get a visualization. Then at the back side you have what we call a back plate or a rear plate, this blue thing. In some of these speakers there is also a hole, because heat gets generated and this hole helps dissipate the heat. So this is what they call vent. Then between back plate and there's another plate called front plate, there's magnet. And then there is also a metallic piece which is this magenta in color, and between the magenta piece and the front plate you have this thin film like thing, and it is called a bobbin, which we talked about in the last class, and on bobbin is wound the voice coil. So as electricity comes into it, AC current comes into it, it goes through and spins around the bobbin and then gets out, and because of electromagnetic induction, the voice coil moves back and forth. As the voice moves back and forth, its motion is opposed by spring force, which is generated by this green thin film called a spider, and it's also opposed by this brown piece of material called a surround, and then you have a rigid diaphragm called a cone, and finally we have a blue membrane called a dust layer. So what's happening is that you have electrical energy, it comes into the system, it gets transformed into mechanical energy, and the transformation is called electromechanical transduction. Then the mechanical energy gets transformed into sound through mechanoacoustic transduction.
What is the basic definition of transducer?
Transducer is any device which transforms one type of energy to another type of energy. So you have piezoelectric transducers where you have electricity being transformed into motion or vice versa. So this is a three-dimensional view of the same object, so you get a better understanding. That is your spider, this is your surround, it's typically made of foam, this is a diaphragm which moves in and out. To close the vent hole, you have this dust cap, you have a voice coil here, magnet is here, magnet is sandwiched between a front plate and a back plate. So I just wanted to give you a brief understanding of how a transducer is constructed, because in next class what we will try to develop is that as electricity is coming in, and it's a signal, it's not a DC current, it has all sorts of frequencies in it. It goes through that winding which has an inductance in it. There may also be an external capacitor mounted on the speaker. So how do you bridge the electrical element of the circuit to the mechanical element to the acoustic element? How do you make that bridge between these three domains, electrical, mechanical and acoustic? Because at the end of the day what you want to know is that, oh, if so much is current is coming into the system at such frequency, what is the pressure I am going to hear? That is what is needed, that is what we want to know. So how do we bridge that gap, and what kind of a theory we should use to understand that fundamental question? So that's what I wanted to share today, and with that I think we will close.